Well, by the clock on the wall, we are at 10:15, so we'll go ahead and get started. And first off, by saying good morning. My name is Kevin Lacey. I'm the Director of Strategic Planning and Programming with the Department of Transportation. I want to welcome you to and congratulate you. You have found the best breakout session of the entire summit. While all the other sessions have been very informative and thought-provoking, I'll say that this one, that they all will fall short of this session. So you need to mark this down in your day in history that you sat in the best summit. So I'm putting the bar pretty high for our presenters. I'm confident that they will exceed all of our expectations. So just a little bit of planning. I'm going to go through, I'm going to introduce the first speaker, and then they'll give their presentation. Then I'll introduce the second, their presentation, then the third, and then we'll hold questions to the end. I will warn you, if you do not have questions, then the three speakers and myself will ask you guys questions. So be prepared. All right. So without further ado, our first presentation is the simulation-based optimization of autonomous vehicle model for mixed traffic scenarios. Dr. Jinkun Lee is an assistant professor at East Carolina University. He received his BS and master's in 1997 and 1999, respectively, in aerospace engineering from Seoul National University. The university's motto is, "The truth is my light." Dr. Lee earned his PhD in industrial engineering operations research from Penn State in 2014. Dr. Lee's current work focuses on autonomous vehicle model optimization based on transportation network simulation. So let's give Dr. Lee a round. Thank you, Dr. Lee.
Hello, everyone. It's nice to meet you. It's my pleasure to share our recent research. This is the core work. Can you hear me? It's okay. Oh, okay. Please let me know if I need to increase my voice. Okay. Yeah. So my name is Jinkun Lee. I am assistant professor at engineering department at ECU, and this is also co-work with Rui Wu. Dr. Rui Wu is assistant professor in computer science in the same university. So this will be the procedure of the talk. Talk briefly about the motivation of our work and some literature review work. And then I will show you what's going to be the research question in spite of the motivation, and I will share the simulation result. And this is still ongoing work, so I understand there will be a lot of questions, and we have still a lot of questions to answer ourselves. So I'll be happy to share any discussion or questions. So the motivation is major vehicle manufacturers are shifting toward autonomous vehicle, and autonomous vehicle specifically, we are assuming it's going to be electric vehicle because every component should be controlled by electric part and controllers. And we already have a lot of ADAS procedure features like smart cruise control or lane keeping assistant to avoid collision avoid assistance. But this is the minimum passive helping system. And what we call autonomous vehicle will be, the example will be what Tesla claims with their Model 3 and above. They are achieving the level 3 or more than level 4, 5, and there is also many companies. Honda is also claiming they are ready to initiate the level 5 prototype soon. So this is the market, and the governments are pushing all the industries to moving from traditional gasoline engine to electric vehicle because of the environmental or sustainability issues. And all the makers know that the whole market will be changed quickly from 2030. And some countries like the EU also prohibit selling new gasoline vehicle from the time. So there will be no doubt that the things will change soon, in a couple of years, maybe within 10 years. And the motivation is, but the problem is, even though all the manufacturers are issuing and selling the new electric autonomous vehicle, the market will be changing slowly. A lot of millions of people are using gasoline car, and I'm not going to sell my car immediately because the government asking us to use electric cars. Maybe it will take 5 more years, 10 more years. So the shift will be gradual. So this will be described by the term penetration rate. The other researchers are saying with the market share change of traditional vehicle to electric vehicle or autonomous vehicle with the term penetration rate. The zero penetration rate means there is no electric car at all. And 100% means whole market vehicles has been replaced with electric vehicle and there is no conventional human drivers anymore. If we are focusing on the autonomous vehicle, and there will be also come with the electric vehicle together. So every electric vehicle manufacturer are thinking about developing this algorithm because just electric vehicle will not be competitive anymore. So they are working with their own research team, or they are trying to M&A some other ventures with specialized in auto driving. So this will be what we expect. But the problem is the autonomous vehicle is good, and that's better than human drivers. That's questionable because it's related to some the real issues with the makers. If let's suppose I am like a company like Tesla, and I am selling and I am promoting the new autonomous vehicle. But if any accident happens, who's going to be responsible for this one? That's going to be the issue and debate between the drivers and maybe its owner and the manufacturer and the insurance company and even government, state or federal government will be involved because of this, a lot of stakeholders are now trying to share their common ideas and issues, and they are trying to build some kind of consensus of how we are going to welcome or accept, be ready to the new vehicle. So there will be still a lot of issues, but my focus is many researchers in this area believe that the manufacturer will take the conservative step at first because they don't want to involve in any trouble with the accident. So the result will be their control algorithm will be also very conservative. Keep long distance between the car to avoid any accident. And what's going to happen to the road traffic? And if any drivers want to interfere my lane, allow them to do that because I don't want to make heated or any collision issues. Then it's going to be like we have a lot of novice drivers in the traffic. The transportation network is the same. We are not going to change the traffic system or road system at all. It will take time. So the road system will be the same, but there will be a lot of new novice drivers, what is called autonomous vehicle. And most of the researchers in this area expect the traffic performance will be deteriorated because of the introduction of the AV. So if we can provide some research on how to understand the complex system, and we can share all these knowledge and ideas and work together with industry and government and any authority with the rule, then probably we can prepare the future a little bit smoothly. That's the purpose of our research. So we use the specific software platform called Sumo. I know that there was other researchers presenting this morning and yesterday, and there is many software platform for transportation network. The BSIMS and the Sumo is one of them, and also there is others. But the reason we choose this one is first, this one is developed by the German Aerospace Research Institute, and it's free. So it's free, so everybody can access easily. But the free means it's not very convenient. It's not very user-friendly. So we have to study a lot to identify how their model is integrated and how we can change the parameters. And if you want to tweak anything, we have to figure out, understand all the code, most of the code. But the good thing is it's open source, so they are allowing tweaking a lot of the model parameters ourselves. That's the reason we choose this platform, because we want to play with the model parameter in autonomous vehicle and see what's going to be its impact. So previous work include some penetration research. And one of the research is famous research is from the Guerrero. I'm not sure how to pronounce his name exactly. I talked with my colleagues who can speak French or Spanish, but none of them didn't figure it out exactly. So please correct me if I'm wrong. But his work is depending on the different penetration rate of 10%, 0, 25%, 50, 75, 100%. He tried to identify what's going to be their impact, the penetration impact on the traffic performance. The traffic performance including the fuel, the time of flow rate, density, and so on, the time to travel. And there is many performance measure. So this is the first research, and he also reviewed many previous papers, how they are connected to this topic. And the next one is he's also used some different models. For the human drivers, this model is using what is called cross model. I know many of you may be already pretty aware of all these models, but I will briefly explain after this slide because some of the parameters are very important in explaining why our work is focusing on them. The human drivers, there is some set parameters. These parameters are derived from the data. So there has been a lot of data of the pattern to identify the pattern of the human drivers, and this model is actually pretty well explaining the human drivers' behavior, and all these parameter values has been derived from the data feeding. So this is something we don't think we can change. But in case of the connected and autonomous vehicle with different level 2, 3, and 4, there was some assumption what's going to be this parameter value. This parameter value usually show this performance is better. They can accelerate faster, and their response time to any accident or hard brake will be more shorter than human drivers, and they can keep shorter distance gap between the car because they can press a brake pedal quickly and efficiently. So they can control more efficiently than human drivers. So these assumptions are pretty reasonable, but our question was, who can determine this value? So we have a question about this. So we try to figure out what's going to be the feasible region of these parameters for autonomous vehicle, given that any of the parameter values should not derive any traffic accident, the safety issues. So the safety issue is taken as the hard constraint, and then we try to identify the feasible region of these parameters, and we want to find optimal value of these parameters depending on the penetration rate. 25%, 50%, depending on the penetration rate, the mix of the human drivers and autonomous vehicle will be different, and we don't expect this will be linear function. So case by case, we want to identify by simulation. And the Sumo is, there is some features of the Sumo, the software. So it's using the OpenStreetMap. So it's very easy to convert and import the traffic network data into the simulation. And there is also many features that help us to find OD, origin and destination matrices and demanding flow. But this is always the question in simulation. How do you define the demand? How many cars will be there? So I will explain it a little bit later. But the simple answer is, in simulation area, there is a term we use all the time, the garbage input, garbage output. So we should be very careful with this input. Otherwise, our result will be also makes no sense. So this is the model plus model. It was published in 1998 as the PhD thesis of him. And after that, he was working in the German Aerospace Institute, who developed the basic, contributed it to the development of the Sumo software. And these are, rather than explaining this whole value, I will focus on some parameters, what these parameters mean. So tau is the time delay or response time. And there will be also parameter of maximum acceleration and maximum deceleration, and also the gap distance and desired speed and whatever. So this will be the key parameters in this model. And another model, which was used by previous researcher for the autonomous vehicle simulation, was what is called the IDM model, intelligent driver model. This one is a little bit different, but it's showing more smooth behavior when we are running in the simulation. So one key parameter is the delta. Delta is to determine the acceleration of the car. The acceleration will be determined by the value A, parameter A. A will be the maximum acceleration or deceleration, but that will be multiplied by 1 minus some factors. And this vector power is delta is the power of the term of the desired speed and the ratio of the real speed and the desired speed. So this inside the parenthesis, this term is always less than 1, and it's powered by delta. So if delta is higher, that means the acceleration will be more smoother. The maximum acceleration is the same, but it's about the behavior of the vehicle. So delta will play the important role in the later study, and there will be also other parameters like acceleration and comfortable, the braking, deceleration, and so on. So based on this one, our question was, if can we maintain the current traffic performance with autonomous vehicle, mixed traffic flow, which one is, that is meaning the mix of the human drivers and autonomous vehicle. So to try to answer this question, we try to change the mix of the different ratio grade of the vehicles and see their impact on the performance. And we also try to find the optimal set of the parameter value of the autonomous vehicle by using genetic algorithm. So this is the simulation screen of the Sumo. Let's skip this one. So our network was focusing on the Greenville area where the East Carolina University is located. And the ECU campus is located here. And in the commuting time, early in the morning, in the late afternoon, there is a huge traffic jams. So this will be the good example we want to focus the simulation. And before starting the optimization work, we try to identify what's going to be the good performance measure that determine the performance of the traffic. So we use the density, the waiting time, and flow, speed, and also collision. The collision will be the hard constraint. In any cases, collision will not be allowed. So that will be the determining performance that maximize or minimize the range of the feasible parameter range. And we changed the penetration rate from 0 to 100%. So this one is the relation between the flow rate in the particle rate, and this is the density. So density and flow will increase linearly as usual, but at a certain point, it will be a little bit saturated and slow down and it's converted to the maximum flow value. And density will keep increase, but the flow will not increase anymore. But depending on the penetration rate, there will be some differences. If they are actually, this is not trivial differences. That's why we wanted to study this problem. And next step was we used the sensitivity analysis. Out of a bunch of parameters, how can we efficiently optimize the performance of the autonomous vehicle? So we want to figure out what's the most important impact parameters that will change the performance. So the change of this one is the penetration rate of 0 and 50% and 100%. And you will see the acceleration. The 1 is the reference value. And then less than 1 means we are lessening the value, and more than 1 is we are multiplying the value. And this yellow curve is acceleration, and with a smaller acceleration, maximum acceleration in autonomous vehicle, we will see the overall flow will be decreased dramatically. So it makes sense because every car is accelerating in the congested traffic flow. There will be the propagation of the jam in the flow. So this will be the reasonable. So out of this sensitivity analysis, we found what's going to be the first, second, and third important parameters, and we tried to pick 5 parameters out of the model and run the GA algorithm, genetic algorithm, to randomly try to figure out the change in the parameters and how they are improving the traffic performance. So based on the traffic performance, the flow rate or the density, we use the reciprocal of them, so that was lower the better. And for the other parameters, waiting time and travel time and others, we use it as it is. So this will be some result of the optimization. After running and iterating more than 100 times, we were able to find what's going to be the parameter set that's making the lowest value of the performance measure. This one is about the density, and this one is about the waiting time. But one thing interesting is the tendency of the parameter is different. They are not aiming to the same region. Depending on the parameters, depending on the performance we are focusing, the optimal parameter value will also have multiple directions. It's not in the same direction. So this one is for the speed and also flow. So they are all different. So our question is again, how can we find the general optimal solution? There will be a multi-criteria optimization problem. So we combine the density, flow, wait time, and everything together. And if the value should be the lower, the better, we use it as a positive value. And if the value should be greater, the better, we use it with negative value. So that this problem or the objective function is to simply minimizing the overall value. And of course, there is the weight for each parameter. So this weight has been taken same for this case, but it should be changed. So if we think the flow rate is more important, we can increase the coefficient, the weighting of this one. And if it's not, we can reduce it. So it's flexible. But what we think this one is a framework. So we want to develop the framework, what we can do, whatever we want. So out of this one, we run the simulation more several times and hundreds of times actually, and was able to find the minimum value of this fitness function. The goal is to minimize the fitness function. And there was some tendency. It's not very monotonic. Sometimes some parameter values are keep decreasing or keep increasing, but some cases it's sometimes increasing and sometimes decreasing. But the direction of this makes sense because, for example, the minimum gap has been increased. This is because we have set the collision as a hard constraint. In other cases, any traffic accident is not allowed by tweaking the parameters. But in case of acceleration value, maximum acceleration has been increased, and deceleration has been increased, and also the delta has been increased. But the high acceleration and deceleration means probably the passengers will feel dizzy. The autonomous vehicle is actually too fast and too slow. But the delta is also increasing pretty high. Delta is the kind of the smoothing factor. So even though the maximum acceleration is high, we think it will not that much difficult. So there should be some modification and more refinement work, of course. But the trend shows this one simulation result is reasonable. And this one is showing some values like the density and waiting time. In this case is the minimum, the better. And the vertical axis is flow rate and the speed. So higher, the better. So if our performance by tweaking the parameter values, if we are aiming to the upper left corner, there will be guaranteeing general better performance, traffic performance. However, the red dots are indicating when accident happened in the simulation. So we set this area as the threshold. Our parameter range should not exceed a certain range so that there should be no accident. So this helps us to identify what's going to be maximum maximum value in each parameter regions, and they will provide us also some basis to study more in the optimization in mixed flow. And we are also trying, this one is the ongoing work. We are trying to use NVIDIA Jetson and their video and image processing to count the number of vehicles passing specific intersection. This data is very important because the input, garbage output, that's the simulation. So we want to use the reasonable value as the traffic flow in our simulation. So this one is the ongoing work. So it's all that I have to talk today. So in conclusion, we are proposing a framework that can analyze and simulate the mixed flow with autonomous vehicle and human drivers. And we assume that the parameter value of the autonomous vehicle has not been set yet. So there is a lot of room to change or increase or decrease, but definitely this will be the common interest between the manufacturers, developers, and also insurance company and customers and also the government. And the penetration rate of the self-driving vehicles show a non-trivial impact on the traffic performance. This is what we found from this study. And genetic algorithm can be used to find optimal value per penetration rate. So depending on the penetration rate, we may probably propose the different set of the optimal value to make our traffic performance reasonable range. And the result of this study has proven that the framework can be implemented to develop the improved behavior model for vehicles. And we had a lot of room to change the weightings in the multi-objective criteria problems and also the parameter set just to identify the maximum range to avoid collisions. So we believe this will be the good starting point, the cornerstone of the study with the similar targets. And this is some references, and thank you. My name is Jin Lee, and please feel free to contact me And if you have any questions or anything to discuss, I'll be happy to answer.
Thank you. As I said, we'll hold the questions until the end. Thank you, Dr. Lee. Our next presenter is incorporating e-commerce related trips in an urban travel demand model. And it's by Samaya Sharma, PhD candidate at NC State University with research interest. Oh, okay.
You can stand by the microphone.
I'll come over here and grab this one. With research interest in studying transportation impacts of AV, CAV trucks, related impacts on the macro and micro level. For those who don't know, the NCSU motto is think and do. When not working, Samaya enjoys kayaking, hiking, swimming, and playing board games. So welcome Samaya up here to present on her topic.
Thank you, Kevin. Good morning, everyone. Thank you for attending. Hopefully you guys are enjoying the summit so far. As Kevin mentioned, I'll be talking about e-commerce related trips and how they can be incorporated in travel demand model. So the outline of this presentation looks somewhat like this. I'll begin by talking about why this is an important topic, what e-commerce is doing to our transportation systems, and then move over to the purpose and scope of this study. There has been some prior research in the area, and I want to highlight a little bit on that, followed by what methodology I'm using here in the study and the results, what conclusions we have, and recommendations for any future work and ongoing future work I have at the moment. So the US Census Bureau said that there's been a 10.3% growth in e-commerce going only from 2020 to 2021. At the same time, there is an increased demand in trucks. The American Trucking Research Institute said that there was about 7.8% increase in just single unit trucks in the past years, 2019. There is a well-renowned survey data that's conducted by the National Household Travel Survey, and they have results from 2017 that say that almost half of their respondents shop once online in every 30 days. We all have seen that in our lives in some way, shape, or form as well. There has been some survey in the Triangle region as well that highlights the fact that individuals are now making lesser trips and they're shopping more online as a result of e-commerce. There is data that says that home deliveries have doubled from 2009 to 2017. And all of this goes out to say that e-commerce is changing the way we shop, the way we behave when it comes to travel. But there is little work that's done on the planning side when we think about how it's changing our transportation system. So that's really the purpose of this study here. Two main things that we have in mind are how can we incorporate e-commerce effects in a travel demand model? And can we do this in a simple, easy way so that it requires less amount of budget and less hours of training for the MPOs? So those were the two goals we had in mind. And the scope of this work is that we've used the Triangle Regional Model. That's actually their team is housed in Italy, and they have a new model up that's called Generation 2, and we've used that. It spans the area that's called the Triangle region, but it really encompasses Raleigh, Durham, and Chapel Hill. And they have three main types of trucks. And the reason why I highlight trucks is because the shift of e-commerce from in-store to online deliveries really means that you're seeing lesser people traveling to stores and more trucks traveling to your houses to deliver goods. So they have three types of trucks in their model, single unit, multi-unit, and light commercial vehicles. And we looked at all three of them for this study. The future year scenario that they have is 2045. And so we use just that for our study. And they have four main time periods, and we looked at all of them, the AM, PM, midday, and night time periods. So like I said, there's been a lot of research in the area, but everyone's mostly focused on how people are changing their shopping behavior. And many researchers have looked at that and they found different findings. Some think that online shopping is actually encouraging in-store shopping. Some find that it's reducing in-store shopping. Some think that it's leaving it unchanged. But I must say that recent literature just points out that in-store shopping is actually reducing as e-commerce is increasing. There has been just one work done by Comey and Nizzolo where they put forward a framework that forecasts shopping flows in an urban area, and they've incorporated e-commerce. But again, this is a totally new framework and they don't incorporate it with travel demand models. Also, this work is in Rome and they have survey data from that city, quite different from our area here, right? So that's the reason why there's need to look into this area. I'm a visual person, so I started my methodology slide with just modules of what my process looks like. And I'll walk you through each of these just briefly, and then I'll talk in more detail in the coming slides. So what this slide shows here is the different modules, and anything that's encompassed in the red boxes is additional steps that we've come up in this methodology. So they were not there to begin with. But I do want to point out that these are outside of the model. So you don't have to really change your model or upgrade your model in order to use this work. And it's a standalone tool. You give it a couple inputs and it gives you essentially OD matrices that you can use to feed back into trip assignment. So what this process really is that it intervenes between trip production and trip assignments. And it will give you additional flows that are happening on the freight side and reduced flows that are happening on auto side as a result of e-commerce. So quickly going through the steps, the first thing is to obviously reduce in-store shopping. So we've changed trip production rates for that. And going forward from that, we needed to figure out where the new truck deliveries are starting from. So it's most possible that they're happening from distribution centers. And so we identified where they would be located in the region. Now that we know where trucks are departing from, we need to make sure that if you shop online, we know which distribution center is serving you. So that's the next step. Following with that is understanding what e-commerce demand is existing at the moment. So we know where trucks are departing from, where they're going to, but how many goods do they actually need to deliver? Once all of this is in place, we want to create tours of trucks, because when you think about e-commerce and deliveries of these goods, trucks are really forming intelligent tours because they're trying to make sure that they service multiple houses in a certain area. And so that's what we did here by creating tours. But we have to split them back into trips because the triangle regional model is still a traditional 4-step model. So it doesn't incorporate touring in it. So what we did was, I think this is really neat. We split the tours into different time periods and we said, okay, there are really these small trips that are happening from origin to destination at these times of days. So they now go back into the new origin destination matrices that you have, and you can feed that into trip assignment, get results. So that's really, this is one slide that summarizes everything, but I'll go into detail of these steps. Again, a visual tool here. If you think about shopping trip rates and reducing them for in-store shopping, what it really means at a model level is shopping is now bifurcated into in-store and online. So by reducing in-store shopping, what we've done is we've diverted that demand to online. So it looks somewhat like this. You're creating a parallel fork for online shopping. How did we reduce these trip production rates? So we looked at the 2017 National Household Travel Survey data for this, and they found that individuals order at least 2.5 times in 30 days, and we used that to come up with online ordering rates for our people in the triangle region. We came up with 3 types of ordering rates, a high, medium, and low, and I'll go into detail of why. Now that we know that, distribution centers were the next big problem to tackle. And we came up with three main types of distribution centers. One is the transloading center. The second is the bulk distribution center. Third is package delivery center. I want to give a couple real world examples to kind of explain what these might look like. And a transloading center is, you can think of it as the biggest facility there is. Something like a Amazon fulfillment center. So they're really big distribution centers that when you click a button and you say, I want to purchase something online, that's the first point that a product moves inside the region and goes from a transloading center to a bulk distribution center, goes on to go to a package delivery center. And that's where the last step happens. The PDCs, or package delivery centers, are the last step of the journey where a small truck departs from a PDC, goes right to your home and delivers it to you. So that's why I have that blue arrow there that says e-commerce flows are actually happening from TLCs to BDCs to PDCs. This figure here just explains the same thing, how this is happening in a visual way in the network, but I have an additional arrow there that says external trips. The reason why I have that is we've actually assumed that all the trips that are happening inside the region are actually coming from external trips. So when you place an order and a product needs to travel to you from a TLC, the products are getting to the TLC actually from outside of the region. And so that replenishment is actually happening this way. We can obviously get rid of this step if you think that your products are local and they're being produced and transported in the area, but this is just more comprehensive. This slide here shows the same thing, but now you look at it just for your house. So imagine you placing an order. This is how it gets to you. Like I explained earlier, there are three types of trucks in the region: multi-unit, single-unit trucks, SUTs, MUTs, and commercial vehicles. So because they are differing in sizes, they can carry more goods. What we did was we said, okay, multi-unit trucks are the biggest. I think it makes sense for them to transport goods from the external region to the TLC versus a single-unit truck takes it from a TLC to a BDC. Light commercial vehicle takes it from a PDC to your home. So that really ties in nicely with the three types of trucks. Now we know which trucks are going from which distribution centers to your houses, all of that. We want to know how many goods we want to deliver using these trucks. And so for this, a neat concept that we used was foregone in-store shopping trips. What this really means is that in our scenario here, say we have a number of trips happening in store, we've reduced them as a result of e-commerce. And the trips that are now not happening in store are actually your demand for e-commerce, right? So that matrix that we get, that's the difference between these two, gives you ODs. And the origin earlier was your house, now it's our destination for delivering e-commerce, right? So that's why this step is important. I mentioned truck touring. So we have an algorithm that makes sure that trucks are delivering these goods in sensible tours to you. And we have a couple assumptions to make sure that it's doing it correctly. Mainly, we assume that a truck is, working 10-hour work days. So the driver is working 10 hours. We used midday travel times to come up with these tours. So we need a distance and we need a travel time. We used an assumption that there's a 15-minute dwell time at each stop. So we want to make sure that it takes some time at the stop to deliver things and then move on to the next location. And in cases where zones are very close by, we wanted to make sure that there is some travel time. So we assume that there's at least 10 minutes between two different zones. Like I said, the model doesn't work with tours. So what we did was we split them back into trips. And we did this also using an algorithm, but we split it into segments of tiny origin destinations happening at particular times. So what this does is we can use time of day matrices and assign them to the network. Our e-commerce scenario here, what we did mainly was we looked up on the internet that which populations are shopping more online. And we found that it's mainly folks that are less than 31 years of age or 31 to 62 years of age. They're the people who are shopping most online. And so we used a high shopping rate for anybody that is in the 31 to 62 year age gap, which is actually a population group inside the model. And then we used a medium online ordering rate for anybody that's less than 31. Folks that are between the 63, 74 year age gap, we used a low online ordering rate for them. So here are the results. The first thing I want to point out is we were reducing flows in the network. We were reducing autos that were traveling. And so we saw a reduced volume to capacity ratio on the network. What happened was, as expected, auto flows reduced in the network and truck flows for all three truck types increased. But at the same time, we have reduced a lot more autos in the network and added relatively fewer trucks by doing this. And so we see that shift is not one-to-one. So that's the other thing. I mentioned truck touring, and what that created was interzonal and intrazonal truck trips. So what was happening was a truck was traveling between a traffic analysis zone to another, delivering your goods and moving on like that. What we did was, if it was traversing between some residences, we did not count those trips, because at a planning level, it doesn't make sense to count that as a trip, you going from your house to a neighbor's house, right? So we did not account for those trips. Here, this graph shows the reduction in auto flows for the region, and you'll see that the links that have dark green color to them are links in the area that saw a reduction in autos. So these are the places that people are traveling less as a result of e-commerce. When you look at this graph here, same thing, but light commercial vehicle flows have increased in the links that have a dark red color to them. So you can see that it's very well distributed in the area, versus when you look at autos, it's fairly contained to freeways, principal arterials. Same things happening with single unit trucks, same things happening with multi-unit trucks. So what does this really mean in conclusion, and what can we do in the future to improve on this? What we thought was useful was to look at these flow patterns and how they're really changing for trucks, changing for autos, and use that pattern as something that helps with policy and funding decisions. We also thought that we should ask better questions as a result of our findings from this work. One thing that we've been thinking about is thinking of e-commerce as really flow of packages rather than flow of trucks in the system. Package returns is a huge point here as well. People shop online and they return a lot of things too. So how can we take care of that? Is it just increase auto trips by 10% when there is 50% increase in e-commerce? How do we do that? Drones, I know drones are a big topic of discussion right now, and medicines, supplies like that are being delivered by drones. So can we include them in the travel demand models? And lastly, just to understand better, because of this problem, I think it's important to think of what really in-store shopping means when it comes to travel demand modeling. What are we modeling at the moment? And what truck travel means in a model. So when we know our basics, we can change the model better for e-commerce. So those are the things that I have on here. And if you have more questions, my name is Soumya. I've done this work with Dr. Leeta Huntsinger and Dr. George List at ITRI. Please feel free to reach out, and thank you so much.
Our last presenter is going to present on the topic of multi-sensor data fusion for signalized arterial performance measurements. Dr. Samander is a research scholar at North Carolina State University Institute of Transportation and Research. He earned both his master's and PhD in civil engineering from North Carolina State University as a Fulbright scholar. Prior to joining NC State, he worked on behalf of the Army Corps of Engineers for 3 years. since we already know what the NC State motto is, we're going to see the Army Corps of Engineer motto is Essayons, which is French for let us try. Dr. Samander is interested in intelligent transportation systems, travel time, reliability, traffic simulation, and connected autonomous vehicle research. Unfortunately, Dr. Samander was not able to be here today, but we're going to have him on a Zoom call. So we're going to be exercising some new but pretty consistent technology from the last 5 years or so.
Thank you, Kevin. Can you hear me and can you see my screen, please?
We can hear you. Give me just 1 second, Shob, and I'll get you onto the screen in the room.
Okay.
Okay, we now see your screen in the room. And if you want to turn on your camera, you can. Otherwise, you will just see your slides.
I believe it is on.
It is on? Okay, let me.
It is. Yes.
Let me there we go.
Trying to figure out how. Okay. All right. Good morning, everyone. Thank you for being here. And thank you, Kevin, for the introduction. As Kevin mentioned, the topic of this talk is multi-sensor data fusion for signalized arterial performance measurement. My colleague, Dr. Nagy Rafael, and I have been doing this work for the past couple of years. I'm not sure if he is or is not there in the room with you guys, but I could not be there because of some flu symptoms that I got last night. A brief overview of what I will be discussing in this presentation today. I'll provide a little bit of motivation for data fusion in the context of transportation engineering, and then I'll talk about development of a fusion framework for signalized arterials, again in the context of transportation engineering, and go ahead and apply that to a measurement, performance measurement in the context of signalized intersection, which is travel time estimation. Then close the presentation with conclusions, recommendations, and some future work. So why do we need data fusion for signalized arterials, or generally in transportation engineering? What does that really mean? What does data fusion mean? There are a bunch of different definitions that can be found in the literature for data fusion. One of the comprehensive ones is that fusion involves the combination of data and information from more than one source. And when we are performing data fusion, our goal is to improve the quality of the information so that in some sense, it is better than it would be possible if the data source were used individually. And nowadays, we know that operating agencies and public agencies have access to a lot of different data sources, and they rely on those for performance assessment of their networks. However, when they're looking at an individual data source, they must consider cost, availability, accuracy, and each of those sources do come with inherent errors and biases, such as if you look at probe data, they're not the population, you just have a few percentage of the traffic stream. They do come with certain errors and biases within them. So instead of relying only on one data source for the performance assessment of their networks, why not combine those data sets to get a better picture of what's going on in the network? That's where multi-sensor fusion can have the potential to produce improved estimates of the performance measures and help out with this issue. This project that we worked on is just in the context of signalized corridors. It's not looking at other transportation facilities, for example, traffic facilities, but there are other ongoing national interests in the topic For example, the NCHRP 08157, which looks at the best practices of data fusion and transportation engineering, and the upcoming FHW publication, which will be a little bit more comprehensive than the work that we have done, hopefully. So I talked about a lot of data sets being available to public agencies and operating agencies. If we look at them at 30,000 feet of elevation, you could probably categorize them into different categories of control data, link data, and trajectory data. In terms of link data, the data sets that are available there are, for example, probe data, sensor data like Bluetooth, Wi-Fi, loop detectors, infrared radars, and things like that. When it comes to the category of trajectories, some data sets that are available at the moment are I2D, MGSAM, data from the sky, which relies on drone videos. Then you have the newly developed connected vehicle data that is available at the moment. On the control side, you have the signal timing plans, split monitor reports, and ATSPM, which is automated traffic signal performance measures that are available to different public agencies and operating agencies. As I mentioned, within the realm of the signalized intersection corridors, agencies tend to have access to multiple data sources. These data sources come with varying data quality and complex data relationships. As a result of that, we believe that a comprehensive data fusion framework is needed to integrate these different data sources, improve the data quality, and be able to capture the complexities of data relationships between different sources and help support decision making. There are a multitude of processes that can represent data fusion, for example, functional, architectural, and mathematical. And in this project, we mainly relied on a functional data fusion process model to deliver the framework, which utilizes disparate data sources for geospatial and temporal fusion of traffic data. Functional data fusion model, it represents the associated functions, databases, and connections that is required for an underlying process. And the framework that we developed has 4 different modules to it. The first one is the geospatial performance assessment module. The second one is performance measurement selection. The third one is the intra-source fusion, and the last one is the inner source fusion. When it comes to the geospatial performance assessment model, the aim of this module is to determine the geospatial coverage of the measures. It is categorized into 2 different levels of system, and where system level looks at collections of nodes, for example, lane groups, approaches, and intersections, whereas the path level looks at combination of both nodes and links, like a corridor. Once you have identified the geospatial performance assessment level, then it's time to figure out the performance measure selection, what sort of performance based on the data that you have available, based on the geospatial context of the network that you have, which performance measure makes sense to go ahead and select those. Once you have selected them, then the intra-source fusion comes in. If you have data sets that are available that have different resolutions, that's where the intra-source fusion comes in. And then lastly, if you have multiple data from multiple sensors, that's where our intra-source fusion module comes in to combine all of those together. A little bit more information on the geospatial data fusion module and how the system level and path level are connected with each other. What we see here, we see an entity relationship diagram that indicates how data with different spatial resolution are combined for a given ATSPM for both the system and path level. For example, if we look at the intersection level, we can see that it is an intersection level performance measure is made up of different approaches, and each of those approaches are in turn made up of different lane groups. And on the right side for path level, if we look at a path travel time, we do see that it is it contains multiple links and multiple nodes. And that's how the relationships are made up here. And also under each of these entities, what we have here are the different performance measures. For example, on the path level, you can see we have travel time, delay, number of stops, average speed, progression opportunities, and so on and so forth. So after development of the framework, it is time to go ahead and apply that to a performance measure. We applied the developed performance measure, developed framework to both a system level and a path level geospatial fusion module. On the path level, we selected corridor travel time, and on the system level, we selected delay. I'm not presenting the delay findings here. I'm just going to be focusing today on just the travel time, which is on the path level. And what sets our work apart from others is the validation piece. We used a data set that provided as ground truth information from the performance measure that we looked at in this context, travel time. And that enabled us to see how the framework that we developed and the fusion that we did is actually performing against different single source data sets. So moving on to the application to signalize corridor travel time, I believe we all in the room know that the importance of travel time is a performance measure. It is typically obtained from a single source, for example, vehicle probe, loop detector, or Bluetooth. And we also know that each of those data sources come with inherent biases associated with them. In addition to that, the different operating agencies have access to multi-source travel time that enables us to do fusion of those different data sources to get a better picture of the performance measure. In addition to that, as I mentioned, evaluation of any fusion process is very important and paramount, and it's very difficult to do that without having access to ground truth data. And as a result of that, we relied on NGSIM dataset for two major objectives. First, creation of the single source data sets, and then evaluation of the individual and data fusion algorithms that we had developed against the ground truth. A little bit information on the study side. When we looked at the path level travel time, we used the NGSIM data set. Again, for those of you that know, it is the data set that provides trajectory of all of the vehicles. And we selected Peachtree site in Atlanta, Georgia. Again, it provides us the full trajectory of all of the vehicles that are available within that time period. 5 intersections make up the entire corridor from northbound and southbound. The distance is about 2,200 feet. The only limitation that we have, and this is potentially a major limitation, is that we only have 30 minutes of data available. All right, moving on to the data sets, what data sets were available to us and what data sets were simulated from the NGSIM data set. The available data that we had access to were ground truth travel time for both the northbound and southbound signal plans that provided a picture of individual cycles and splits, and also volume of each of the signalized intersections. However, we didn't have single source data sets. As a result of that, we went ahead and simulated those data sets, for example, Bluetooth, fixed sensor, and probe vehicles. And the green data sets that you see here are the data sets that we fused together to get the enhanced travel time information. And we relied on RMSE, MAPE, and MAE for the evaluation of the fusion process. In terms of the fusion algorithms, we can categorize these into two different categories of algorithms. So we have the simple algorithms like linear regression and simple average of source travel times, whereas on the other side, we can categorize it as data intensive modules, models, or algorithms like artificial neural network, random forest, and k-nearest neighbors. We use these, and we're planning to use a number of other algorithms like common filter, Dempster-Shafer theory. However, due to the constraint that we had, which was the limitation of the data set, we were not able to apply those. But these are the algorithms that we were able to apply in this context. Moving on to some results that we have. Again, this slide shows the error analysis, comparing the errors in individual sources versus the fused algorithms. So the mean ground truth travel time that we had for the northbound and southbound on Peach Street was about 135 for northbound and 119 seconds for the southbound. The graph that you see here, there's two different groups of algorithms or data sources, if you will. On the left side, we have the individual data source errors, which is Bluetooth, probe vehicle, signal, and loop detector. And on the right side of the graph, we have the different fusion algorithms. We have the simple average, linear regression, k-NN, and random forest, and ANN. On the single data sources, we see that Bluetooth is providing the lowest error. However, on the fusion algorithms, all of the algorithms except the simple average provides better travel time compared to ground truth travel time, and ANN is the best performer among them. We can, from this figure, we can conclude that the fusion gains depend significantly on the algorithm that we select for fusion process. We also looked at the impact of data availability on performance. So we, on the larger scale, we looked at all of the data sets that are available and fused and put them together. But what if we don't have those data sets? What if we have just Bluetooth with, let's say, loop detector data, or we have the probe data with the Bluetooth, and how would that impact our fusion process, and does that really significantly impact our process or not? And what we found out is obviously that the more data that you have available, the better and improved performance you will have. We found out that Bluetooth data set provides adds the most value compared to other data sets, and signal timing, loop detector are the least that add value. And again, it's because they have a lot of inherent errors associated with them. However, best combination depends on the algorithm that we selected. Again, going back to the previous slide, that choice of the fusion algorithm is very important. Some key takeaways: we saw that data fusion produced improved estimates of travel time in the context of signalized corridors. We saw that the outcome of the fusion process highly depends on both the fusion algorithm and data availability. To some extent, some of the limitations of the work that we presented here is limited data set, as I talked about it. And as I mentioned, that there are some fusion algorithms that are very data intensive and require a lot of data than what we had. And also the potential for errors and biases in the simulated data sets. Although we try to mimic the inherent errors that are associated with a given data source, we may have not been able to incorporate 100% of them. For example, for Bluetooth data sets, we know that there are these location detection errors that need to be considered. We did that based on the previous data set that we had available to us. But again, we might have not incorporated the true quantity of the error for the location detection. Moving on to some concluding remarks, we saw that signalized corridor performance measures benefit significantly from the fusion of available data fusion of available disparate data sets. We saw that arterial travel time benefits from presence of Bluetooth data set significantly. And we saw that the improvement levels of these fusion algorithms depend significantly on, first, the availability of the data sets, what data sets are available to us, how many are available to us, and what are the errors associated with those data sets, the data size, and also the selection of the appropriate fusion algorithms. Some future direction for this work. The first one would be application of the framework to a real world scenario where we have multiple data sets that are collected simultaneously. For example, you have Bluetooth, connected vehicle, loop detector, signal plans, Wi-Fi and pro vehicle data sets, and also having access to ground truth data. We can't really emphasize enough on this because if you don't have that, you're not able to comment and quantify the performance of your fusion outputs. And the second direction would be to investigate transferability of the framework to an uninterrupted flow facility with freeways. With that being said, thank you for your attention. I'd be happy to take any questions that you may have. Thank you.
All right, we are at the question and answer time. Hard to get out there and I thought it was in. So we have any questions from the audience? Remember, if you don't have questions for us, we have questions for you. All right, let me bring the mic to you, sir. Thank you.
Right, so I had a question for you. I guess your data for the last research that you did, was this, how much of the data was from that pandemic timeline, and would that affect your outcome on your research?
Thank you for the question. Data that I used for the study, really one data point comes from the National Household Travel Survey that we've used to come up with the online ordering rates. I wouldn't say that it's pandemic related. It's a little bit before pandemic. If I can check what year that data is from, believe a little bit before pandemic. But yes, the literature that I cited saying e-commerce has grown, some of those points like US Census Bureau and the Triangle Regional Survey where it says people are shopping less in store, some of that is coming from the pandemic. Hopefully some of it is still true. Yeah, so.
Any other questions? Yes. And who's your question for?
So you were saying that you found the personal vehicle trips going down and the truck trips going up. Do you know, or does the literature yet know the net impact on VMT in general? And I'm also curious about impact on emissions, since the trucks might have greater emissions than the cars.
That's that question. I have several ones.
Thank you. Yes, we did look at VMT impacts here in the study. I didn't share those results, but VMT impacts really have occurred as a result of e-commerce. Like I said, we reduced a lot of auto trips and we added very small amount of truck trips. So that's also one reason why you see a lot of VMT gains happening from that. It's still, I would say, we have to look at it a little more detail because this has a lot of assumptions built into it. And surely emissions, we have not looked at emissions, but yeah, I'd love to explore that side of it because we have the data that gives us results. So looking at it from a resilience standpoint, looking at from emissions will be good. We haven't looked at it though.
Any other questions? I got a question for Dr. Lee. How does your model consider the aggressiveness or passiveness of human drivers I know, when you look at truck drivers, they'll often leave, considerable headway, but that aggressive human driver will infill that space.
Yeah, thank you for the question. It's a great question, actually. So it's a still a hard problem. In case of the human driver model, we are using the data. So from the data, we used all the parameters. So we have not much variation with aggressive drivers and passive drivers. But I had similar question before in other conference. So we, when we are providing the optimal set value of the autonomous vehicle, the question was, the human knows the autonomous vehicles are now getting aggressive. So the population of the human drivers will also change their behavior. Then what are you going to do? I couldn't answer frankly right now, but we must have collected more data and we have to adaptively change our model. I think that's the best we can do for now.
Thank you.
I have a question for you, Dr. Lee. Great presentation. I know we talked a lot about car following and Kevin asked a question about truck. What about lane changing?
In the sumo model, there is also part of the range changing model. So we are using 2 parameters, and I didn't explain that in the presentation, but we assume the traditional, the conventional range changing model, but we focused on the car following because it's what we feel more aggressive or passive to understand the behavior of the system. But definitely, that will be also we need to consider in.
Any more questions? Autonomous vehicles will help with autonomous, aggressive drivers. Yeah, it'll help with, inattentive drivers, drunk drivers, all those, they will no longer be drivers, which sounds like a good thing. All right, I want to give kudos to Dr. Samander as a practitioner in a state DOT, recognizing that the cost of additional data is not a trivial item. You know, that's as a state traffic engineer for 18 years. I had lots of folks come up with ideas of getting more data. And when you start looking at the more data and the more cost attached to it, it was often significant impact. So thank you for that. All right. For everyone to get your PhD credits and all that, you have to tell me what the motto is of the Corps of Engineers. I told everybody the answer earlier today. It was essay on, which means let us try. I figure I wouldn't ask NC State because we probably have a couple of NC State folks here, but all right, we're gonna give you a couple minutes back, and if you've not signed in and you want your PhDs or your professional development hours, please sign in the back and carry on. Take care.